Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the second lecture of week 2, and we will continue from where we left in the last session. Alright, so we have discussed already the fundamental shapes in the case of Cartesian coordinate system for all the three cases that were for one dimension, two dimensional and three dimensional coordinate systems, and we had already discussed a lot about that in the previous section, in the previous lecture. Alright, so any coordinate, let's say 1:1 or -2, 1 signifies what in two-dimensional Cartesian coordinate system, that it actually gives us two fundamental shapes. One is x equals -2 and the other is y equals 1. In this case, we have discussed so far about formation of line using the fundamental shapes, which were two-dimensional planes. In the case of three-dimensional Cartesian coordinate system, we had already discussed about that. How a line is formed, we had already discussed about that. But how a point is formed should be discussed. So in three-dimensional space, we say that a point is formed by, can we say, intersection of two lines? Yeah, technically that would be correct. That would not be false, but as I said before, that every other shape should be defined in terms of the fundamental shape. Only then that will be accurate and there won't be any redundancy. Why? What do we mean by redundancy? That if we define somehow that a line is formed by intersection of two planes, then a line is a line is formed by intersection of two planes and a point is formed by intersection of two lines. It means that essentially there are generally there are four planes involved in formation of that line, which is not true. Actually there are three planes, three orthogonal planes, which are involved in the formation of a point in three-dimensional Cartesian coordinate system. And in terms of fundamental shapes, we would say that a point is formed at the intersection of three orthogonal planes in the case of 3D Cartesian coordinate system. Again, I would give this example in which we have got a plane x equals to constant, a plane y equals to constant, the right one, and a plane z equals to constant. These three planes, where they are intersecting, they are forming a point, one corner of this rectangular box. So the definition of a point would be intersection of three orthogonal planes, three planes at which the point at which three planes meet gives us the point. Okay, so you can imagine that you can extend this plane, you can extend that plane, and you can extend the bottom plane, and these three planes, these are basically infinite planes. The area of each plane is infinite, so wherever they will meet, wherever they will intersect, there will be a point. Okay, so we can say that a point in three dimension is given by three coordinates x1, y1 and z1, and this point P, let's say, is formed by intersection of three planes which are x equals x1, y equals y1 and z equals z1. Okay, so if I would like to write the coordinates of the point formed by x equals x1, x equals 1, y equals 2, and z equals -2, I would say that the point formed at the intersection of these three planes, let's say that point is Q, will have the coordinates 1, 2, and -2, which actually means that this point is formed by three fundamental planes, which are x1, x is equals to 1, y equals to 2, and z equals to -2. Okay, so one important point is that obviously earlier we were using two planes to form a line. Now this time we are using three planes to form a point. So as long as you're at that point, you are simultaneously at all the three planes. As long as you are at this point, you are simultaneously on this plane, you are simultaneously on this plane, and on this plane as well. Okay, and the important take home message is, at the point of intersection where this point is located, we can say that this point is located at the intersection of three orthogonal imaginary planes. Remember that all the planes that we are talking about in 3 dimensions, or all the lines which we are talking about in 2 dimensions, these lines and these planes are imaginary planes. Imaginary means they are not made up of any matter, they are just there in free space. You can imagine these planes, but these planes has got no physical meaning or no physical substance attached to it. Okay, so what I can say is that a coordinate system gives you a point, and points are defined in terms of fundamental planes, and actually these coordinates are what? These coordinates are actually the addresses to that to reach that point, address to reach that point from where? From the reference point, origin. Just like I gave an example in the last class, that if someone calls you and asks you for the direction which leads to any university, you will the first question that you will ask would be where are you right now, and you will take that point as the initial reference point or origin, and you will try to direct that person with respect to that point, and you will say go in that direction so and so kilometers, and in that direction so and so kilometers, and you will reach your destination. So to locate a point, we need to have an origin. Okay, so if we are here and someone asks us to give us the coordinate of this point, you will say to reach this point, move in the direction of x, how many units? 1 units. Move in the direction of y, how many units? 1 units, and you will reach this point. So the address of this point is 1, 1. So if someone asks you to reach this point, if someone asks you to tell the address of this point, you will say okay, start from origin, from the reference, okay, and move in the direction of the minus x, how many units? 2 units, and then move in the direction of y, how many units? 1 unit, and you will reach your destination. So if in 3 dimensions someone asks you to give the direction, to give the dimensions, or sorry, coordinates of the point which is located somewhere here, and let's say this corner is origin. This corner is origin means the corner at my end is origin, means this plane or the plane at this very back, this plane is x equals to 0, this plane is y equals to 0, and this plane is z equals to 0, the intersection of these three planes will give me origin or the reference that would carry the coordinate values of 0, 0, 0, because with regard to this point, as I said, that x1 y, a point x1 y1 z1 means it is an intersection of x equals x1, y equals y1, z equals z1, then origin is actually nothing but origin O is actually nothing but intersection of three planes, x equals to 0, y equals to 0, and z equals to 0, 0, 0, 0. So let's say this portion from which we pop out our tissue papers, this is x equals to 0, and this one is y equals to 0, and this one is z equals to 0, then these three planes joined together or intersecting each other at the point of origin. And if we want to locate the point, let's say point this point, okay, and let's say the coordinates of this point, the coordinates are 1, 3, 2, then you would say, okay, you're to reach that point P, which is this point, start from origin and move in the direction of x, how many units? 1 units. Then move in the direction of y, how many units? 3 units. And move in the direction of z, how many units? 2 units. And then you will reach this point. So this would be the address of that point, which point is the combination of or the intersection of three different planes: x equals x1, y equals, sorry, x equals 1, y equals 3, and z equals to 2. So now we have discussed the definition of point, and just now definition of origin. We had already discussed right-handed and left-handed coordinate system, and now we have already defined the position of an arbitrary point, which by this example 1, 3, and 2, or x1, y1, z1, address of P, which is this. And now we'll move towards the definition of differential volumes, differential surfaces, and differential elements, differential lengths. So how do we define a differential volume or differential surface? I'll get back to you within few moments. So now consider this pair of axes, or the set of axes I should say, x, y, z, and consider this point whose coordinates are x1, y1, z1. What does it mean? It means that to reach this point we should reach an imaginary surface which is intersecting x-axis at x1, and which is perpendicular to x-axis and also parallel to y-z axis. So from origin we will move in this direction, and let's say this point is x1. We have reached this point. So you should imagine now that there is an infinite plane parallel to y and z axis but perpendicular to x axis, but I am not showing that plane for the sake of clarity, but you should know that that plane will intersect. I am just drawing a line, however that will be an that will be a plane. I am just drawing a line here. That plane will intersect x-axis at x equals x1. Similarly, now it says that to reach this point, this address, we have to move in the direction of x, x1 units, then in the direction of y, how many units? y1 units. Let's say we have reached this point, which is actually, let's say this one was y1, and then move in the direction of z, how many units? Let's say z1, yeah, z1 units, and let's say, yeah, this point is z1. So if I move 3 units upward, 3 divisions upward, I will reach z1. Okay, so again you should know that when you would reach at this point, there would be an infinite plane which will be parallel to x and z axis, and that will be intersecting y axis at y1. Yeah, that will be intersecting y axis at y1. So there will be another plane which will be intersecting y axis at y1, and that plane would be parallel to xz plane, just like this. Okay, earlier the plane which would intersect x at x1 will be this plane. This is z, this is x-axis coming towards you, x-axis. So this plane, or the plane at the back, you should consider the plane at the back. Plane at the back, let's say that plane is intersecting x-axis at x1. All right, okay. All right, so the plane which will be intersecting y at y1 will be parallel to x and z axis. So this plane is something which is qualifying for xz plane, and since we have got y axis in this direction, you can extend this and you can see that this plane will somehow intersect somewhere on y axis. And as we reach this point, now before reaching this point, at this point there are two planes intersecting each other. One plane is intersecting x-axis at x1, the other plane is intersecting y-axis at y1. So actually what situation we have is this plane at the back is x equals to x1, this plane is y equals to y1, and these two planes are intersecting at one point which is parallel to z-axis and which is forming this corner line. Okay, this corner line. But as soon as we moved upward, how many units? z1 units. We reached certain point. And that point is lying on another plane now, and that plane is z equals to z1 plane. So we have got three planes: x equals x1, y equals y1, z equals z1, and at the intersection of these three planes we have got this point. So there are three planes associated with this final point P, which you should always remember, but we never draw those planes because then the diagram would be very messy. Okay, right, let's say we have another point Q. The coordinates are x2, y2 and z2, and the relation is such that x2 is obtained by adding a differential amount in the x1, y2 is obtained by obtaining a differential amount by adding a differential amount in y1, and z2 is obtained by adding a differential amount in z1. z2 is obtained by adding a differential amount in z1. So you can say that let's say x1 is 1, y1 is 2 and z1 is 3. So probably x2 will be 1.1 and this will be 2.1 and this will be 3.1. just to give you an idea of what I'm talking about. But remember that these differential entities are way too small to be quantified by any number. We cannot quantify it by any number. These quantities, these differential quantities are very, very small. Okay, so let me use a different color for that. Let me use this red. I hope you would be able to see that. So if I want to reach this point Q, I know that this if I want to reach the surface which is intersecting x-axis on x2, I have to increase a little bit of length, that which is dx, very small length, in the previously previously obtained value of x1. So if I'm here, I know that I am at the point P whose coordinates are already given. So I am already at x1, by the way. So if I want to reach x2, what I should do, I should move in the direction of x. How many units? x1. I'm already at x1 plus some differential unit, and let me call that as dx. So if we move in the direction of x from already point P, if we move in the direction of x, how many units? Dx units. Maybe we will be able to we will be able to reach a plane which will be intersecting x-axis on on x2. So this is not that clear, so maybe I should embolden it. So just consider this to be a line, so we reach here somewhere. Okay, now let me just remove these additional lines so that the diagram don't get any messier. And now if I have to reach, our target is to reach point Q. To reach point Q from P, what we are doing, we are using this relations, which we just came to know somehow, that x2 is is equals to x1 plus dx, y2 is y1 plus dy, z2 is equals to z1 plus dz, and so on. So if I want to get y2, if I want to reach the plane y equals y2, I have to just add dy and y1. Okay, so when I'm here, you can see I'm using a different chalk. From transition from here to here, what change I made, in which coordinate did I change the direction? And that direction was x. So I can say that, okay, let me redraw it. Yeah, I moved from here, I moved in the direction of x only. So at this point we have got the same values of y. The value of y will be y1. Okay, the value of y will be y1. We just moved in the direction of x alone, so the values of y and z should remain the same. So in order to reach y2, we just have to move in the direction of y. We are already at y1. We have to move in the direction of y certain units. This is y1, and how much we have to move in the direction of y? That is dy. So the length of this red line is dx. Length of this blue line, I'm writing here, it is dy. And now to reach the plane z2, when we are at this point, we are already on x2, y2, the plane x equals x2, the plane y equals y2, but still we are on the same horizontal plane which is shared by this point and this point, because we haven't moved in the direction of z yet. So to reach the plane z equals z2, we have to move in the direction of z. How many units? How many units? Dz units, okay? Because we were already on z equals z1. So we just added dz units in the original plane. So we reached another plane now. So what is the situation here right now? Let's say this corner is point P, where the back plane, this plane is x equals x1, this plane is y equals y1, this plane is z equals z1, and all the three planes are joining at point P. Okay, and now in order to reach so this point has been made by the plane which is, you know, the flat plane which is towards me, not towards you, and the bottom plane and the plane on the right. Okay, and in order to reach point Q, what we had to do, we had to move in the direction, because we are already, we are here, we are already at x equals x1. So if just we move certain distance here, so we are now another plane, that plane is x equals x2, okay, horizontal plane. All right, so but still we are sharing what? We are sharing the same y equals y1 plane and z equals z1 plane. Even we have moved at this point, but we are still sharing y equals y1 and z equals z1 plane. Only the flat x equals x1 plane has been changed to x equals x2 plane now. So after that, after moving in this direction, in the direction of y along this blue line, we have reached this corner. Now we have reached to another y equals constant plane, and that y equals constant plane is this now, because now this point is no more related to y equals y1, this one plane. But still you can see that this point is still at that z equals z1 plane. Okay, this point is still formed by x equals x2, y equals y2, but z equals z1 plane intersection. Okay, but now if we move in the direction of z, that is along this yellow line, okay, we will reach at this point. Okay, now this point is formed by three different planes as compared to this point. This point has got a new z equals z2 surface, and this point was at z equals z1 level. This is higher as compared to this one. Okay, so now these 2 points P and Q are now have been formed using entirely different three planes. Okay, this one with x equals x1, y equals y1, z equals z1, and this one with x equals x1, y equals x equals x2, y equals y2, and z equals z2. And if I ask you that what is this length, you would say this length is dx, because we have to move dx unit to reach from x1 to x2. And how much is this distance? This distance is dy. And how much is this distance? This distance is dz. Okay, so now these planes, these points are actually are constituted by 6 different planes. Okay, so and you can see that those 6 different planes are actually enclosing a volume. These 3 different planes, and these 3 different planes, these 3 planes and these 3 planes are in all the 6 planes are infinite in extent, but these 6 planes combined together planes combined together are enclosing of a finite volume, the volume of this box. Okay, so I can say that the differential volume, because the sides are very small, this side is extremely small, this side is extremely small, this side is extremely small, obviously extremely small, something which is extremely small multiplied by another thing which is also extremely small multiplied by another thing which is also extremely small forms some volume which is extremely small. And you can tell me from your basic mathematics geometry that the volume of this tissue paper box will be dx dy into dz. This length multiplied by this length multiplied by this length. So this is the formula for differential volume in 3-dimensional Cartesian coordinate system. This is a standard formula. How it came, I just told you. So whenever you find somewhere in any equation or any integral, you find this dV, differential volume, and you are working in a 3-dimensional Cartesian coordinate system, you will simply replace this dV by dx, dy and dz. Okay, so we have discussed differential volume. Now differential surfaces, obviously if this is differential volume, then this differential volume is actually enclosed by 6 differential planes. Okay, 6 differential planes. So but there will be 3 differential formulae for each plane. Okay, because the area of this front plane is same as the area of the back plane, area of the top plane is same as the area of the bottom plane, and area of the left plane is same as the area of the right plane. So let me just say that this plane over which the value of x is constant, let me represent that plane, plane or surface, which will be differential surface, obviously formed by differential height and width. So the surface is also differential. The differential means extremely small. So differential surface, let me call this differential surface as dsx, surface at which the value of x is constant, and this is formed by dy into dz, dy into dz. Similarly, this differential surface, the left one or the right one, will share the same formula, and that is dx. Let me represent that differential surface by dsy, and the formula for this will be dx multiplied by dz, dx multiplied by dz. And for the top one, if I just say that this is dsz, you don't need the formula. If you see the symmetry here, you will simply say the formula for this will be, okay, for constant x, dy dz, because x is constant. Okay, so the variation is in the direction of x, direction of y and direction of z. For constant x, changes are in the direction of y and z. For constant y, the changes are in the direction of x and z. For constant z, the changes are in the direction of x and y. So these are the formula, but incomplete formula for differential surfaces. Why incomplete? We'll discuss momentarily. All right, so the differential lengths are simply dx, dy and dz. Or if I want to ask you the distance between this point P and that point Q, P and Q, distance between these 2 points, and you already know the width, the height and the length, so you would say that the differential length, let me call the line which is joining this point and that point, obviously that line will go within this tissue paper box, okay, a straight line, and let me call that differential line because that line will be very small, let me call that differential line dl. So you can use the distance formula to find that out, and you can write it like this: depth square plus width square plus height square under root. So this is differential length between 2 points, or these dx, dy and dz are also differential lengths. So we have also discussed this. Now point number 6, unit vectors. If I ask someone, if any student, what is a unit vector, he would simply say a vector which has got a unit magnitude. Okay, that's true, but I'm not talking about any vector, any unit vector. Let's say we have got a vector r. If I ask you to give me a unit vector in the direction of r, you will say that simply divide this r by its magnitude, you will get it. Okay, but I am not interested in that. Right now we are trying to establish a coordinate system. Okay, we are not solving a particular problem, we are trying to establish a coordinate system. So the definition of unit vector should be universal to that particular coordinate system. So all right, that's true that the magnitude of a unit vector is always 1. That's true, but there are actually 2 properties of a unit vector. That unit vector is always, if we have got 3-dimensional coordinate system, there will be 3 primitive unit vectors, okay, in whose terms every other vector or component of vector or any other general unit vector, like I just wrote here UR, it can be defined. Okay, for Cartesian coordinate system, you all know that we have got three unit vectors, primitive unit vectors, I, j and k. And if I ask you to give me the direction of I, j, k, you will simply say this is the direction of I along x-axis, this is the direction of j along y-axis, and this is the direction of k along z-axis. Okay, but is it always the case? No, it is not always the case. The direction of I happens to be in the direction of x-axis because of certain properties of unit vectors. Unit vectors have got 3 main properties. Number 1 is a trivial one, so we are not going to talk about that. And that trivial property is that its magnitude is unity. Okay, granted. But what about 2 other things? Actually, the unit vector I is defined as, or I, j or k. A unit vector is always, a primitive unit vector is always perpendicular to the fundamental shape with which it is associated. Number 1, it is always perpendicular to the fundamental shape with which it is associated. Number 2, it always points in the direction of increasing values of that coordinate. मिसाल के तौर पे, for instance, if I take I and we say that I is pointing in this direction, I is pointing in this direction because I should be a unit vector which is perpendicular to its fundamental shape, that is x equals constant. So x equals constant is a plane, is a YZ plane intersecting x at x1 and or at any constant value, and is perpendicular to x axis. So x equals to constant is already perpendicular to x axis. We have talked about that. Similarly, y equals to constant, x equals to constant is perpendicular to x axis, y equals constant is perpendicular to y axis, z equals to constant is perpendicular to z axis. So what properties did I just tell you about this I, j and k, or primitive unit vectors? I, j, k are primitive unit vectors. Any unit vector other than I, j, k will be defined in terms of I, j and k. Okay, let's say I've got a unit vector, a vector r, 2i plus 2 j plus let's say 2k. Okay, so in order to find a unit vector in this direction, you all know we have to find its magnitude. So 2 to the 4, 2 to the 4, 2 to the 4. So what we have got is 2 under root 3, is it? So the unit vector in the direction of r is r divided by vector r divided by its magnitude, and you would say that, okay, if I just divide these two quantities, I will get under root 1 upon under root 3 I plus 1 upon under root 3 j plus 1 upon under root 3 k. This is a unit vector, no doubt about it, but this unit vector is being defined in terms of these primitive unit vectors. So because we are defining a coordinate system, we are not interested in this definition. This definition is true for every coordinate system, but what we are interested in is defining the primitive unit vectors in which every other vector or every other unit vectors can be defined. Here we see that this unit vector is defined in terms of these primitive unit vectors, and also this vector r, which is not unit vector, is defined in terms of those primitive unit vectors. So defining a primitive unit vector, a set of primitive unit vectors is always important, or the definition of all or the process of defining all these primitive unit vectors always becomes a point of interest or point of study when we are defining or talking about a certain coordinate system. Okay, and if we are talking about three dimensional coordinate system, so there will be 3 primitive unit vectors. So the definition which I just told you about the primitive unit vectors, not definition, properties, they've got unity magnitude. They are always perpendicular to their respective fundamental shape, and they are always pointing in the direction of increasing values of the coordinate. Okay, so for this fundamental shape, if I want to define a primitive unit vector, I should define a primitive unit vector which is always perpendicular to x equals to constant, and which always points in the increasing values of x. So what could be the more correct point than the direction of x-axis, because x-axis is always perpendicular to all the planes which are formed by x equals any constant value. And now if first property is fulfilled, now we are left with 2 options: either go in this direction or go in that direction, because both directions are perpendicular to x equals to constant. But the second property tells us that it always points in the increasing values of the coordinates, so it will always point in the increasing values of the coordinate. Similarly, for a primitive unit vector for y equals to constant, the primitive unit vector should always be perpendicular to y equals to constant, and it should always point in the increasing values of y. That's the reason why it is sheer luck that we got the primitive unit vectors in the direction of x, y, z in the case of 3-dimensional or 2-dimensional Cartesian coordinate system. This is pure, I would say, luck. Otherwise, things would have been different if these 2 properties were not met. Okay, So now I just told you that these formulae are incomplete. Yes, they are incomplete because differential surfaces, the formula for differential surfaces is not a scalar quantity, it's a vector quantity, unlike this volume or this length. By the way, I just gave you the I'll talk about that later on. Okay, so dsx is equals to dy dz. It's a tradition or it's convention in vector analysis that we give direction to the surfaces. Okay, we associate a direction to the surfaces. Okay, so associating direction to volume does not make any sense, but to surfaces it does, and the convention is to always associate the direction of the surface which is perpendicular. The direction of surface is always perpendicular to that surface and is always pointing out of the volume. This is convention. So let's say this box is the volume. So for this surface, the direction will be perpendicular to the surface and always pointing out of the volume. Okay, and for the back surface, this surface, again the direction of the surface will be perpendicular to the surface and pointing out of the volume. Okay, and for this surface, meaning dsy surface, where the value of y's are constant, the direction of for the right one is perpendicular to the y equals to constant surface and pointing out of the volume. It cannot be like this because it is pointing into the volume. And for the left surface, y equals constant surface, the direction of this surface is perpendicular to the surface and pointing out of the volume. Same is the case with these surfaces. Okay, so if we are talking about this surface, the formula for differential surface will be, in this direction we have got ax, for the top we have got, for the top where z is constant, we have got the direction perpendicular to the plane and pointing out of the volume, which is the z direction. And for the left or for the right, where the y is constant, we have got this. So now all these differential surfaces become what? Vector quantities. Okay, differential surface. And by the way, for the back surface, I just have to append a minus sign here, which will become here, and for the bottom surface I'll have to append a minus sign here, and for the left surface I just have to append a minus sign over there. But generally, if we don't consider the minus signs, this is the way of writing differential surfaces. Differential surfaces. Okay, so differential length, I just gave you one thing. Differential length, the distance between 2 points P and Q. But what if I ask you to give me a differential vector which could take me from this point P to that point Q, this point P to that point Q? Can I get any differential length, a vector in the vector form? Yes, I can. To reach at that point, I can say that I have to move in the direction of x, how many units? Dx units. So if I move in the direction of x, how many units? Dx units. And in the direction of y, how many units? Dy units. And in the direction of z, how many units? Dz units. If I add all these together, I will get a vector differential length which will show me from here, which will show me the direction from here, point P, to that point Q. And since This differential length is formed by very small differential values. So yeah, this dl, the formula for differential length, will be this, and this differential length will be very small. See you in the next lecture, inshallah. Thank you very much. Allah Hafiz.